Okay, next continue our lecture. Okay, so first let's start from the Boolean model. Okay, in Boolean models, we will assign the documents in each the terms in each document by using the weights. It's either 0 or 1. 0 means it's a percent. The terms is not shown in the document. 1 represents the term is in the document. And in the Boolean models, we can express our query with the Boolean operators like and or not. Okay, so we will use it according to the query, then return all the documents satisfy your query. So it's some Boolean operators. Okay, use or and not. Here I give examples. It's unstructured data. I want to use this example to answer the following questions. Which plays of Shakespeare contain the words Brutus and Caesar, but not Caponia? Okay, I want to, if you know Shakespeare, he is a mystery. So he wrote many plays, many famous plays, like do you know some of the plays? Yeah, Romeo and Juliet, and others. Yes, I know they are very famous, right? But yeah, like okay, I will show you later. Here are some like Anthony and Cleopatra, Julius Caesar, The Tempest, Hamlet, Othello, Macbeth. Okay, so and Romeo and Juliet. Yeah. So here we can collect all these documents, all these plays here, and all the terms. You can consider it like a dictionary. So a dictionary is here, and if these terms like an anthem appear in this play, in this document, we will show indicate it with 1 here. Okay, so you can see 1, 1, 0, 0, 1. You can understand. So what's the word? The words appear in the first and second, but not and also in Macbeth, but not appear in the third, fourth, and the fifth. So we call it the turn document incident matrix. And to answer the query in this form, okay, how to calculate? Okay, so first we take the vectors from the Brutus, Caesar, and the Caponia. Okay, so we just the Brutus here we take its vector. It's a 0 and 1, 1, 0, 1, 0, 0. And the second is Caesar. And also the Caponia. We take the 3 vectors. Okay, take the 3 vectors, and but remember the Caponia, we have a not equation here. Okay, so we perform a complement for the vector of Caponia, then do a computation between the 3 vectors. So the 3 vectors will be is for the Brutus here, and there's a Caesar, and the complement of Caponia. Then you perform a bitwise calculation here. It shows the 1, 0, 0, 1, 0, 0. So this means the answer. If 1 means the first play, it contains, it satisfies your query, and also the false document. Okay, so you can check it back. The first document. The first document contained Brutus, Caesar, but not Caponi, right? And for the fourth document, it contained Brutus, Caesar, but not Caponi. Okay, so the idea is, although it's very simple, but is such a matrix is too large. You can imagine if you have 1 million documents and it contain 10,000 words, you will build a very large. For example, you have so many documents and terms. Actually, you will build a very large matrix in this form. Okay, for example, here just give you examples. Okay, so in total you will have your matrix will be very big, like half a trillion of zeros and ones, but most of them are zeros. So it's a very sparse matrix. So actually you don't need to store such a matrix exactly. We should use a smart way to store this matrix. So it's called an inverted index. Okay, inverted index is a very good strategy to deal with the extremely sparse matrix. Okay, so you can convert, would only record the ones for each term. Also here, for the Brutus, for each word, okay, we only keep which document it contains the words. Okay, we just make a record here. The first plane, the second plane, the fourth plane, and all these planes, they contain Brutus. Okay, so it means you don't need to keep the 1 million documents. Your vector cannot, you don't need to keep a 1 million vector. You just keep only dozens entries in your list. Okay, so for the second, for the third, okay, so for all dictionaries, we generate an inverted index like this. We can also call it a post-it. Okay, now I show you the process, how to build the index structure. Okay, so first you collect the documents, is to be indexed. The documents including the following terms, following documents like the friends, romance, and the country name. And then we perform a tokenization. We throw the tokenizer. So we will remove we only keep the English words. Okay, remove some symbols here. Okay, so now we keep only the friends, romance, and the country names because they are tokens. And through some linguistic modules, we can modify these tokens to a unified representation like this for all friends. You just transform it into friend, convert it from the plural to single, and all transform into a lowercase like this. Okay, romance transform to romance, country name transform to country name. Okay, so just apply some linguistic rules so that to make they have as a unified representation for each word. And then finally, we then, based on these tokens, to build, for each token we build their inverted index in this way. Okay, so here is document 1 and document 2. We take the two documents as an example. So we transform it through the tokenization. We transform it into this. Okay, so then after tokenization, then we generate their index. So first we just read each token and then list it. But we list all the terms here, and also we keep their document ID here. For the I is from the first document, and the next word is D. Okay, D is also from the first document. So we just arrange your terms and also keep their document ID. So next we do the sorting according to their alphabet order. Okay, so you can see the ambitions now become the first. And the next is B and voters. Okay, after this, then we can build the posting, the index structure like this. You can see we just do some aggregation and count how many times the terms appear in the documents, in this document set. Okay, so you can see the first terms, ambitious. Here is this number indicates the frequency. Okay, 1 means it appears in only one document. Okay, and we also keep is posting list here, which means ambitious is shown in the second document. And the next is B. B is also appear once and shown in the second document. And the third term is the Brutus. The Brutus appear twice. Okay, so the frequency is 2, means it appear twice. It's appear in the first document and the second document. Okay, so you can see Brutus show here, it appear twice. So just aggregate them together. Okay, and make a final posting list. Okay, so all the terms you just aggregate to generate the final posting list like this. Okay, any problems? Okay, so after you generate the index structure like in the posting list in this way, so we can consider the query Brutus and the Caponia given a query like this. How to find their documents? Find a document that contains the Brutus and the Caponia. Okay, we just find the two lists. For Brutus, okay, is the list, posting list here, and for Caponia, and then we can compute their intersection between them. Okay, note that these two lists are already sorted according to their document IDs number. Okay, so it's sorted, and then to compute their intersection, we can start from their first posting. Okay, so if not match, you see, if they not match, so we can check which one is smaller. If for the smaller one, you can advance to the next, like this, and then you find, okay, they are matched. So our intersection find the second document contain the Brutus and the Caponia, and we can continue to the next to do the matching. Okay, go on, and now here you find the 31. They match again. Okay, so you can output the result. Okay, we just follow, and until if anyone list they reach the end, they cannot go further, then you can stop. the search process. And this is our answer. The second and the 31 documents, they contain our query routers and the component. And it's actually it's a linear search time, okay, based on your posting list that. And the type complexity is very, you can consider is actually it's very fast. It's a linear complexity. And we consider another problem. If there's a best order to process the query, it means if your query contains several terms with end, okay, maybe we can consider which method can make the query to be processed very efficient. Here is an example: routers and the component and the Caesar. Okay, so if you perform the query, we perform the routers and the component, use their intersection, and then end with the Caesar. The result is actually the same if we perform the query for the second and the third term first, and then use their result to perform the end with the first term. The result should be the same. The order will not influence your result, but they will influence your search time. So why? Okay, so you see here we have three terms list here. You can see the routers and the component, they contain a long list, but for the Caesar, their list is relatively short. Okay, so if we want to follow the previous way to compute the intersection between the two lists, so which way you think can be processed in a very efficient way? So what should be the best order to make it, and we can have a very fast search? What do you think? Which two should be processed first? Caesar? Caesar and the component. Why? What's the idea?
Because Caesar is quite short, and when you component is about 60, you got the combination, the extra the result between the computer and Caesar, you can with the computers, you get only 4 indexes.
Yeah, because the Caesar is very short, right? So it means we can expect it can be finished very fast, right? Okay, so if we compute the component and the Caesar first, so the result at the most is 2, right? And you can use, it's still very short, so you can use it to compute the third term, and maybe it can be finished very early, right? Okay, so yeah, it's right. So thank you. Okay, so actually we should use the short list to do the search first. Okay, you can compute. You can use this with a very long list to compute the intersection first, and use the result to compute the routers. You change the order will not not influence your result. Yeah, but it can make your search more efficient. Okay, so here is the algorithm. Okay, so process in order of the increasing frequency. So that's why you remember we in our previous slides. in our slides we keep the frequency here. So show us, it's just indicated the length of the positive list of each word. Okay, so we just keep. Okay, keep the frequency here and start with the smallest set, and it can cut quickly. Okay, so we can execute the query as a Caesar and Brutus or Camponi. I think both are okay. And then next with the others. Okay, here show a more general optimization. So if your query contains all, okay, like this, so meeting or crowd, and the no or stripe. Okay, how to estimate what will be the best way to process the query. So if you use and in the previous example, we showed that we should use the smallest frequency first to process it first. But how about all? Actually, all you have to make you can use the frequency to count, also to estimate how many documents will be shown in your O operation. Okay, so actually, if you deal with the O operations, you have to estimate the size of O's by some of this frequency. It's a conservative calculation. Okay, so here is an example. You have tangerine or trees using O. Okay, so for this tangerine and O trees, so here the tangerine here, its frequency, its words, the frequency is this, and the trees here. So for these two terms, they use O to do the calculation. So we estimate the document size of the O should be the sum of the two frequencies. It's okay. It's a conservative estimation. And for the others, mother and all skies, okay, you do the same thing. Here, you just sum the frequency. And also the last one. The last one is you just sum the same, the two terms together. And then because they use n to do a calculation, so you just follow the same way to find the smallest frequency. Okay, to optimize your query order. Okay, so in this case, I think you can calculate by yourself. Okay, just find which one they have the smallest frequency and then use it to do the calculation for n. Okay. Okay, so let me make a summary for the Boolean queries. So it's a successful as a primary retrieval tools for decades. So and for some professional searchers or like lawyers, they still like the Boolean queries. So because you know exactly what you are getting, okay, you can use a very long query terms, and they can return you exactly correct documents for you. Okay, so in Boolean models, we use these binary decisions and no partition. And it's good for the expert users. But however, most users if for the general users, because they don't know the much details, they don't have don't know such a background knowledge, so they will feel such a bully models is difficult to use. Okay, the problem is like this. Let me show you an example here. For example, query 1, here I use the standard user D-Link 6050. Okay, in the search system, and they just returned the 200,000 hits documents for you. Too many documents for you to browse it. Okay, so maybe you can try to add some extra terms here. No card found, but now he returns 0. No documents match all the terms. So you can see it's difficult to modify your queries to find a suitable size for you to browse this result. Okay, will be too many or just 0. It's too difficult to control your query. Okay, so it will take a lot of skills to generate your information need into an appropriate query to find a manageable number of hits. So later I will tell you the ranking list, ranking models to address this problem. Okay, so let's take a break for a while.